No, that's the wrong one. Now we got it right.
Do you want the green button?
Oh, yeah. Let's hope I make it in time. So hi everyone, welcome back. And by the way, thanks for the perfect transition, because next talk is exactly about what you asked for, temporal structures for human activity recognition. And before I start, let me first thank my collaborators who are all here today, Alexander Richard, Anna Kukleva, and Jürgen Gall at the University of Bonn, where most of this work has been done. And to give you an idea, my work is actually, and I go a bit back in time, but I think it's very helpful. My work is all about how do we get from action classification to real activity understanding. And when I talk about action classification, I mainly refer to a principle that we usually want to put a label on a short trimmed clip or on a frame, whatever we have. And that this kind of concept obviously brings us into trouble when we have like 5 or 10 minutes of video, because then when we just consider one frame, it's probably not going to tell us the whole story, and just putting one label on 10 minutes also usually doesn't make sense. So what I usually care is about what happens after you get your classification score for each single frame, and how can we learn representations that somehow capture the structure of those complex activities. And the task that we usually use to kind of evaluate what we are doing is nowadays called temporal action segmentation. There have been some other names around for a while, but the idea is pretty simple. You have a long, pretty untrimmed video, can be 5 minutes, can be 10 minutes, can be up to 1 hour, and you want to put a label on each frame in this video. For this task, it's obviously very helpful to know what's going on like a small and large temporal scales. And we have built a lot of systems over the years who managed to do better and better on this task. But when I was just compiling this talk and just thinking about how can I put everything in one slide, it turns out that we have a very consistent pipeline with components that always show off no matter which system we build. And this is that we always have some kind of low-level representation. So you can, in the end, you can use your frame-wise classifier for that one. And this low-level representation usually has a temporal input window of 1 or 2 seconds. So roughly 20-30 seconds is what probably most people are using. I mean, some networks can extend it more, but this is like the standard size that I guess most people are playing around with. And then it turns out it's a good idea to have some mid-level representation in between, for which we sometimes use state models, sometimes use explicit length model in terms of like decay functions, or just a combination of both. And those mid-level representations usually can capture a few seconds up to some minutes. And then what also always comes is some high-level representation in form of an action grammar, where you actually try to combine all those building blocks together. And then for this high-level representation, this is actually where you model the activity sequence and where you can model like your 10 minutes, 1 hour, whatever you need. And the glue that kind of holds all those pieces together is actually temporal inference. So we always assume that we have an input sequence X, like your frame-wise classification score, and that we want to recognize a state or action sequence S. And in the end, we're just doing this by finding the maximum probability that certain action sequence X is generated by our input. And to do this, we actually use some kind of temporal inference or dynamic programming. So we just get an input sequence and we try to find the best path that actually maximizes the probability for this sequence. And by finding this best path over time, we actually get like 2 things. We first get the classification, of course, for each frame, but we also get the temporal segmentation, because obviously when we have this path, we can easily say, okay, at this frame we have been this class. And it turns out that this model can handle also long temporal sequences pretty well, because we have this implicit segmentation and classification at the same time, and we don't separate those two problems. But it can also do a bit more for you, and this is actually the interesting part. First, you can do any kind of continuous or online learning, because your hypotheses are just based on beams, and you decide how long you want to go for. And what's probably even more interesting, the mid-level thing, this mid-level action modeling can actually capture temporal variations in the actions. And those temporal variations are very important, because we have two flavors of them. First, we have intra-class flexibility, which means that in usually kitchen scenarios, you will always have actions which are shorter, like pouring coffee is always 3 to 5 seconds, and longer actions, like frying egg, will always take like 1 minute or more. And it makes a lot of sense to kind of model this mean action length not in the feature, but in some higher level modeling space. And this is actually what we do with either having, like, for example, more states, or having a different action length prior for our actions. And then the second important thing is that we have a lot of inner class flexibility when we have actions. So when you think of yourself, in the morning, you're tired, you need to get the first cup of coffee, you're just getting to a cupboard, opening it, taking the cup, it takes a while. Versus imagine yourself, same action in the afternoon, you're in a hurry, you need to get to the next meeting, but you urgently need your coffee, you can assemble the same task in half of time probably. And this difference in action length happening a lot, and in our model we can kind of contribute for that by having all the self transitions respectively by just stretching the length prior a bit. And this is actually very helpful. And this is a very old evaluation, but I wanted to bring it up anyway because it shows a bit the problem that we run into, or that we ran into and we still run into. So this whole thing of temporal modeling actually mainly doesn't make sense when you have small action clips. And we gathered a lot of action data sets that we had at this point. They're actually a bit sorted by the length of the overall data set as well as the length of the clips. And usually we need at least 6 to 7 hours of data and a certain length of the action that those models make really sense. When you are below this, just go with your preferred linear classifier, it will always do a better job. But when you have like real large action sequences and real long action sequences, like 70 hours of video or even 200 hours of video, then modeling those stuff on top actually will help to make your old system better. But it's also a problem when we want to continue in doing research on that, because even labeling 70 hours of video is a nightmare and more doesn't make sense. And this is why we actually decided to look at weak learning of sequential data. And the idea here is what many people already mentioned. At some point you cannot annotate more data anymore, so you need to come up with smarter ways to train your system. And this was our approach to make the system available for like smart training. And the idea here is you are given a sequence of input data, like your video streams, and then you are not given the frame boundaries, but you're only given the transcripts for each video. So you know the actions and which order they occur in the video, and your job is actually to infer the boundaries during training. And the first system that we had, and it's a bit simple and naive, but it's worth understanding anyway because it's like the basic of everything that comes later, is you just have a simple bootstrapping approach. So you say you take all your videos and you take the transcripts, and then you just split all the videos uniformly according to the actions that you have in the transcripts. And actually, obviously this is pretty wrong, and we did some statistics. We have around 20 to 30% correct frames in this training data. But you say you don't care, train your system anyway, and then we can actually do what we are good at. So we just take the video and the transcript and we try to infer the temporal boundaries for this transcript. And from better boundaries, we obviously can train better classifiers, so we have some kind of like an iterative system. And let's say at least it worked. Then we, of course, had some nice ideas how to improve it. Next stage was to replace standard classifiers by recurrent models. And What we also found out in this like middle stage of this whole process, what was very important is that we also adapt the action length. So in the first model, we mainly kept it as it was, usually with like 3-stage action models. But at some point you realize it's actually a good idea to kind of have more states for longer sequences and less states for shorter sequences. And we tried to include this in the learning process. That was very helpful. And then, of course, we want to make it end-to-end, using mainly the decoding loss to train the recurrent network. And you can see with each system, we kind of improved by roughly 5%. Actually, last jump was even like 10%. By the way, best numbers are at the moment 45% on this task from a paper from Stanford. And what's actually like the interesting take-home message of this whole exercise is not the pure numbers, but the ablation study that we did for one of those systems. And for this ablation study, we thought, okay, for the weak learning, we are kind of doing okay-ish, but not very well. So what tiny hints of information could we actually use to improve the results? And it turns out that you don't need a lot to get a lot better. And the first experiment we actually had was with just using the transcripts and then assuming that we would know the ground truth length of each action. So I told you we already had the impression that when we adapt for the action length, we are getting better. And now we assumed, okay, what would happen when we would know how long an action usually has to be? And it turns out by just this piece of information, you can actually increase from some 30% accuracy to 51. So it brings you already like a step ahead. And then the second thing we tried, because this was also kind of like a realistic idea, what would happen when we would have sparse frame level annotation? Because sparse frame level annotation is much easier to get than full frame-based click stuff. And it turns out when we have a very small fraction of the data set actually labeled by sparse frames, like I'm talking about 10,000 frames out of 3 million, this even helps more because you're not only getting transcript information from your sparse frame labels, but you also get additional boundary points that can help you during decoding. And overall, the fully supervised version would run at 61%. At the moment, best fully supervised system is at 65% from this year's CVPR. So this was kind of like the interesting things that we found. And with that one, I come a bit to the current works that we do. We obviously understood at some point there are no transcripts for videos out there, so it's much more reasonable actually to look at what happens for unsupervised learning of temporal sequences. And I hope you have seen Anna's poster in lunch break. We also tried to find better alternatives for unsupervised feature learning, especially in Hebbian learning. So when you're annoyed of backprop, please ask me. But what I actually want to tell you about is that we had the idea, okay, we can learn from sparse labels, so let's try to learn from video subtitles. And so the question is, oh, can we learn from video subtitles? And to make it short, the answer is mainly no. And just to elaborate this no a bit more in detail, we had the idea that we want to do a weekly or weekly supervised learning from subtitles because, of course, there's like huge YouTube data available. And would be nice if we could just mine this content. But to figure out if we are actually able to do this, we thought it would be good to have some common data ground. And this is why we collected actually a data set, which we refer to now as mining YouTube data set. So it's a bit small. Let's say it's not as big as the biggest ones, but this was actually intentional, so universities can still handle it. You don't need a GPU cluster. So the idea was to just go to YouTube and to look for action videos, and actually not some random action videos, but we especially looked for all kind of instructions for egg recipes. So we mainly have like scrambled egg, pancake, fried egg, egg roll, omelette. So it's all one domain, which makes it on one side harder, but on the other side you get more redundant classes, which is good. And overall we had like 20,000 videos that we found with subtitles. From those ones you get like 350K training samples, and for testing we actually have 250 videos which are fully hand labeled. And we found out that the only task that actually makes sense on this kind of data is temporal alignment. So you're already given the order of the actions and you just need to find the right boundaries. And I will later explain you why this is the only way, or the only good way we found to evaluate such data. We use the Jacquard index for evaluation, and we provide frame-wise features on GitHub. So when you're interested, just go there and download. And as I'm a bit running out of time, I just come to the challenges that we found in this kind of data. And it turns out that it's the expected and the unexpected that you have here. First of all, obviously there's a lot of noise. So we did some statistics, and only 50% of the clips that we gather will actually have the action in it that they're actually labeled for, which is not much. But the probably even bigger problem is that when you go to natural language labels, you end up with a lot of language inconsistencies. And that's, like, in my impression at the moment, a real nightmare, because you get a lot of hononymies, which means that you have one label, but they refer to different tasks, like add pepper can be the bell pepper or the grounded pepper. Sometimes you know, sometimes not. And you have polysemies. For example, we have 4 classes, which is mix egg, whisk egg, beat egg, and scramble egg, which doesn't make sense, but they are there because it's like free language mining. Of course, you have high intra-class variation and long tail distribution, and you still have to deal with untrimmed videos. And putting all this together is obviously a mess. And it turns out that a lot of stuff that we tried doesn't work on this data. So the list of things that doesn't work is actually very long, and the list of things that works is very short. But just to answer some questions, we looked a bit at let's say, what does large scale help, or to which extent does it help to have more training samples? And it turns out that just accumulating more samples will always give you like an improvement of roughly 2%, but that's it. So it's not as big as one might think. And at some point there are even limits to the scale of YouTube. But what actually helps a lot, or what was like one of the few things that actually worked in this context, was some kind of semantic embedding. So what we actually tried is we constructed a semantic hierarchical tree that kind of captures the relations between actions and brings those closer together. And it shows that when you just run inference on this tree, you can actually improve results a lot. So I guess making sense of semantic groups of things might help in this case. And this brings me to the conclusion. So what's missing? The answer is definitely not more annotated training data. And in terms of what are the missed opportunities, I'm a bit surprised that I'm the only one who has POSE on the list. Perhaps if you want to see POSE as another expert system, it might make sense. But I also think that understanding POSE would take a lot of workload of the real cognition systems that we have to train with so much data at the moment. And POSE is actually pretty advanced, so it might be a good idea to make a bit use of what's going in this community. And of course, as I'm working on the connection on many fields anyway, I think it would help a lot to see beyond clip classification and see what's going on in speech, but also robotics. So when you need to generate human actions, you get a completely different viewpoint on the problem. Perception, of course, as we have Jeff here, reasoning, causality. So there are a lot of fields that we can learn from. And the major challenge is the one that everybody has mentioned here, that we definitely need to learn more from less annotation in some way. Okay, thanks.